In this video, I want to talk about sequential switching and unbounded responses. So whenever you have a circuit that has more than one switch and the switching happens more than once at different times, we call it a sequential switching. So let's just, for example, take a look at this circuit that we have here. We have a voltage source, 4 ohm, 12 ohm, 6 ohm, 3 ohm, and 18 ohm resistors, one 150 millihenry inductor, and two switches. So as you can see here, this switch goes from the closed to the open position at time equals t0, and this one goes from closed to open position at time equals 35 milliseconds. So the way that we solve these type of circuits is by finding the initial values at the times of switching for the capacitors and inductors in the circuit. So if I want to draw the several versions of this circuit at different times, so if we assume that this circuit has been in the original position for a long time before t equals 0, we know that the inductor acts as a short circuit. So I can say at t equals a little bit before t equals 0, the circuit that we have is like this. So we have the voltage source, these two resistors, we have the first switch in the closed position, we have these resistors, so we have 4, this one is 12, this one is 6, this one is 60 volts, and let me just put the unit as well, and this one is 3 ohm. We know that the inductor is now acting as a short circuit, so I just simply write it as a draw it as a simple wire, and then we have this 18 ohm resistor, and here you can say we have switch 1, here we have switch 2, both in the closed position. So we know that VL is 0 because whenever the inductor is a short circuit, that means that there is no voltage across it. But IL is not necessarily 0. So we have this current that we need to find, and this would be the IL at time t equals 0. But now when at time equals 0, switch 1 opens, the circuit that we have is going to look like this. So for time between 0 and 35 milliseconds, our circuit contains this 6 ohm, this 3 ohm, the inductor, and then this resistor, and this is switch 2, which is in the closed position. So by opening the first switch, this part of the circuit is now eliminated. So we have again VL and we have IL now, but to solve this we need to know what is the initial current at time t equals 0, and we should be able to solve this. But we know that at time equal 35 milliseconds, this switch would open as well. So for any given time greater than 35 milliseconds, the equivalent circuit that we have is going to include the 3 ohm, the 6 ohm, and the inductor. Now again we have VL, we have IL, but now to be able to solve this circuit we need to know what was the current at time equal 35 milliseconds. So as you can see, because we had two switches, we are actually solving three versions of this circuit at different times. So this is the concept behind sequential switching. One thing that you should always remember is that anything but inductive currents and capacitive voltages can change instantaneously at the time of switching. And this is derived based on the general equations that we had for the inductor and capacitor. So we know that for the inductor, V equals L di over dt. So the current cannot change instantaneously because that means we should have infinite amount of voltage, but the voltage can change. Similarly, for the capacitor, we know its current is C derivative of the voltage with respect to time, which means that the voltage of the capacitor cannot change instantaneously because that requires infinite amount of current, which is not physically possible, but its current can change instantaneously. The other thing that I wanted to talk about was with regard to unbounded responses, because so far with the circuit that we have seen, we always had exponentially decreasing functions. But there are cases that a circuit response may grow rather than decay. So this is what is called as unbounded response. And this is possible only in the circuit that contain dependent sources. Because if you remember from the general equation that we had, the exponential function was negative t over tau. So what should happen so this exponentially decreasing function become increasing? If tau, or the time constant, is negative, then this exponential function, so e to the negative t over tau, increases over time. But for tau to be negative, we know that the time constant for an RL circuit was L over R, or the time constant for an RC circuit was RC. So for tau to be negative, the value for the resistor needs to be negative. So this happens only when we have circuit that dependent sources. Not always, but when it happens, we usually have a dependent source present. So in such circuit, the Thevenin equivalent resistance with respect to the terminals of the inductor or the capacitor may be negative, which generates a negative time constant, and the resulting current and voltage increases without limit. So let's just take a look at this circuit for now. We have this capacitor 5 microfarad with the initial voltage of 10 volt, and it is connected, it gets connected to this circuit at time t0, because this switch goes from the open position to closed position. So what this circuit contains of, we have a 10 kilo ohm resistor, a current controlled current source, and a 20 kilo ohm resistor. So this current controlled current source has the equation 7I delta, and I delta is the current that goes through this 20 kilo ohm. So let's just find the Thevenin equivalent resistance of this circuit. So for doing that, if you remember from before, we could apply a test voltage with a test current, and we show or find the relationship between the two, and that gives us the Thevenin equivalent resistance. So this one is I delta, this one is 7I delta, and this one is 10. And let's just assume we have a test voltage, I call it VT, that creates a test current that goes through this circuit. To find the relationship between VT and IT, what we can do is that we can write the node voltage equation at this node. So I call it node 1, and I just say KCL at node 1. So if I do that, what I get is VT divided by 10 plus, let's just go for this current, this is VT divided by 20. So the current that goes through this 20 kilo ohm resistor is VT divided by 20 kilo. So that makes this 7IT to be equal to, let me just put it with the negative sign because it is entering the node. So negative 7 multiplied by VT over 20. And then we have this IT which is also entering the node. So negative IT equals 0. So if we rearrange this equation, what we get as RTH, which is VT over IT, to be negative 5 kilo ohms. So we see that the Thevenin equivalent resistance of this circuit is negative 5 kilo ohm. So now if we connect this inductor to this circuit that has a negative 5 kilo ohm Thevenin resistance, what we have for the voltage, here we call it VO. If you remember, it was the initial voltage, so voltage at time 0 multiplied by e to the negative t over tau, which will be voltage at time 0, which is 10, e to the negative t over tau. Tau is R multiplied by C, so or RTH multiplied by C. So since RTH is negative 5 kilo, what we basically have is negative 5 multiplied by 5. And for now I just eliminated the units, right? But you can consider them too. This 5 is 5 kilo ohm, this one is 5 microfarad. So this whole thing is going to be 10 e to the negative t over 25 milli, or let's just put it as 25 10 to the negative 3. And now this power becomes positive. Why? Because we have a negative sign for the resistor. So as you can see, the final equation is 10 multiplied by e to the t over 25 milli, or 25 multiplied by 10 to the negative 3. So as time increases, this exponential term doesn't decrease. In fact, it is also increasing. So this is what we call as an unbounded response. So ideally speaking, this response can go to infinity. But usually in actual circuits, the response eventually reaches a limiting value. Why? Because the physical components that we use in the circuits, they have physical limits. So for example, what if this capacitor breaks after the voltage across it becomes a certain value? Or this dependent current source, depending on how it is being created, it may have a saturation state, right? So even though the ideal equation tells us that the voltage between these 2 points can go indefinitely, but in reality, if we have a circuit like this, it usually gets to a point that it cannot go beyond that, whether a component is breaking or whether we hit some saturation state. But nonetheless, this is an example of an unbounded response. In this video, we learned about sequential switching, and also we learned about unbounded response in RC and RL circuits.